This is a basic exponential function. What makes it an exponential function is that the variable is in the exponent. So we often have equations that have exponents, but they're not exponential functions because the exponent is a number. So those are polynomial functions for the most part, or they could be radical functions. But when the exponent is the variable, that's when you have these exponential functions. And it's asking for the y values for y equals 2 to the power of x, and you're given the x values. So we're just going to put x in the place, or the x value in the place of x to find the corresponding y values. When we go 2 to the power of negative 3, that comes out to negative, or sorry, not negative. It comes out to 1 over 8. That's 2 to the power of negative 3, right? When you do 2 to the power of negative 2, that's 1 over 4. 2 to the power of negative 1 is 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. And then 4 and 8. And then if we plot those points on here, it's going to show us what the graph of y equals 2 to the power of x look like. And it actually looks like that. When you see a function that has that shape, you should recognize that as an exponential function. And we're going to work with these type of functions enough that you will start to recognize those. But then it does ask you for this other information. So domain, range, x-intercept, y-intercept, and asymptote. What would you say the domain of this is? Yeah. Any real numbers, right? So you can write it, there's lots of different ways to write it. X is an element of the set of real numbers. But what about the range? Y is greater than or equal to 0. Okay, I said greater than or equal to 0, but it actually should just be greater than 0, right? Because, and I'm just going to scratch that out because I can't erase it. Because it doesn't actually come all the way down to 0. What's the x-intercept for this one? None? What about the y-intercept? At 1. And the asymptote? 0. X equals 0. Or y equals 0. What's the asymptote? The x-axis, right? So y equals 0. For the second one that you have, it's going to be very similar. It's y equals 3 to the x instead of y equals 2 to the power of x. And so your values, 3 to the power of negative 3 is going to be 1 over 27. And then 1 over 9, 1 over 3, 1, 3, 9, and 27. And the graph looks like this. The domain, same thing, right? What about the range? Same. So y is greater than 0. What about the x-intercept? Same, there's none. The y-intercept? Same, it's at 1. And the asymptote? Same. So the fact that we changed the base from a 2 to a 3 didn't change any of these characteristics of the graph that we're talking about. It did change the way that it looks, right? It increases more steeply than the other one with the bigger base, but it doesn't change those basic features of the graph. And then you also had these ones, which I just have the graph of. Y equals 1/2 to the power of x. That one looks a little bit different, right? But the domain and range are still the same. The x-intercept y-intercept and asymptote, all that stuff's the same. And the same thing with this one, y equals 1/3 to the power of x. So those things that we talked about, all those features of the graph, are the same for any base exponential function. So one that hasn't been transformed. You should know what its domain and range is. If it's just some number to the power of x, they're all going to be very similar. Some positive number to the power of x. If we start changing it, then we start looking at transformations, and some of those things can change, right? Like you can imagine, what if I took this graph, y equals 1/3 to the power of x, and then I said +1? What would happen to it? It would go up 1, right? So the asymptote would change, because it's also going to move up 1. The y-intercept would change. The other things are not going to change for that one. If I did y equals 1/3 to the power of, and in the exponent I put an x plus 1, what would happen? It's going to move over which direction? If I put a +1 with the x. It's going to move to the left. So again, the y-intercept would change. The rest of those features would stay the same. The next question that you had on there is to write the function that corresponds to this graph in the form y equals b to the power of x. So it gives us some points on the graph, and it tells us it's going to be y equals b to the power of x. So I guess we just need to figure out what b is, right? The x and y are going to stay as x and y. But let's look at the points that we have. Here is an xy and another xy. So if I do use that equation and fill those in, 64 is equal to b to the power of 3, and 16 is equal to b to the power of 2. Can you figure out what b is? 4. So that means 4 to the power of 3 is 64, is that correct? And 4 to the power of 2, is that 16? So b is equal to 4, which means the equation is just y equals 4 to the power of x. So that was really just figuring it out by guess and check. But how could you algebraically solve one of those equations? If you take the cube root in the first one of both sides, you get what b is equal to. If you take the square root in the second one, you get what b is equal to. But actually, when you do that, you get positive or negative 4. Does either one work, or does it have to be 4? What would the graph look like if it was negative 4? It does have to be positive. If it's negative, the values are flip-flopping from positive to negative based on what the exponent is. If it's even, it's a positive number. If it's odd, it's negative. And so it does not make a graph that looks like that.